Hello everyone. GM. Today even more morning, or maybe earlier, afternoon or your evening, or maybe not if your time zone changed to you. Okay, first, I would like to apologize. I should have sent out a warning, or I should have called this out last week, last Thursday. I forgot. Sorry about that. And I was hoping for an announcement in the Discord, but I don't see if Encode posted. I should have sent you an email though, because we had a time zone change in London, in UK. So, for example, here in Brazil, we don't have summertime anymore, daylight saving times or anything like that. So, for me, the boot camp is starting 1 hour earlier. Okay. Don't know about you there. I see that we have like 18 people here. Usually we have 40, 50, so probably, unfortunately, there's going to be a lot of people late. So if you're watching this recording later, I'm sorry about that this happened. I have little to blame because I forgot to remember you all last Thursday, but you might have received some emails on this too, right? Okay, yeah. There was a warning about this in the first day. I don't know if you recall, but it was a while ago. So maybe a lot of people are going to watch today's lessons by recording. Okay. But for all of you that are here watching this recording later or are here with us now, let's start on lesson 17. We just finished the bulk of this bootcamp up to the third week. You got the hang of it for building smart contracts. Of course, you weren't like senior smart contract developer yet, but you got a hang of it. You have the tools, you have the syntax, you have everything that you need for getting started. You could be competing hackathons and all. Last week, we stopped this path of exploration on the EVM Solidity part to do a 1 week of full stack development, doing the front end, back end, oracles, and all of that. And now we're going to combine these two paths with or goal or end goal of building a project at the end of this bootcamp by giving you some additions. Okay, so this week and next week, this bootcamp is going to branch off into different subjects. Up to this far, it was like the root of the knowledge, the bases, and the trunk, like a metaphor in a tree, right? The trunk of it. And now we're going to branch off. Today, we're going to see gas optimization, smart contract security. We're going to introduce the concept of these. We're going to see the size of these fields so that we know how to study them later. Next lesson, we're going to see about gas limits and about loops. Then we're going to see about randomness. Then we're going to do a lottery. The next week, we're going to speak about scalability and then DeFi and then upgradability and then peer-to-peer networks, security toolset. There are many different subjects, separate subjects that we're going to speak. Not necessarily one after the like it's not like every lesson is going to use the previous lessons now. No, this was up to this far. You got the idea, right? We were in a sequence so far. Now I'm going to start branching off in those different subjects, right? To get you started with everything that you need for your final project. Every of these lessons are going to be useful and required for you to be a good smart contract developer, blockchain developer. But it's not like we're going to have a sequence of the same subject like we did in the past 4 weeks or so, okay? It's going to be branching off in a lot of different and fun things for us to experience every day. Today, we're going to start with optimization, gas optimization. We're going to say exactly what I'm going to speak, what you're speaking about on gas optimization just in a while. Before we begin, I want to show this little library ether.js, and we're not going to do a whole study on this like we did on VM. We're going to just see as an overview because Ethers is going to do the same things as we do in VM. Okay, actually, Ethers came first, and then VM did it more for the front end side now, but we can using in other places, of course. And ethers, if you look at the documentation, is the same thing as VM, a library, complete and compact library for interacting with the Ethereum blockchain. Same thing as we would do in VM. Everything that we could do in VM, we should be able to do in ethers, okay? And there are only some differences. When using the contracts, when deploying the contract, instead of having that contract object, we have this contract factory object, which is an object used to deploy smart contracts, for example. Those little differences. So it's basically doing the same thing with two different packages. I'm going to use these packages for future lessons, for today's lesson, for upgradability lesson. So it's going to be useful. Am I sharing the screen? Let me see. Yes, Simon, so might be a problem on your side. Is my screen visible for everyone, right? You just check that
Yes,
before
yes.
proceed. Good,
Yes.
good. Thanks for confirming, Johnson. So ethers is going to do everything that we would get from VM. We're going to do today's lesson with ethers. I'm going to show how to set it up. Okay, I have this folder where I had all of the previous projects. I'm going to create a new project called project 6 or whatever. And we're going to use this folder for today's lesson. So cd project 6. And I'm going to do those same steps for initializing hard. Remember, npm init. I'm not going to copy over the files. Okay, I'm just going to start a new project because I'm going to pick a new option now. npm install save dev hard. And then I'm going to do hard init in that folder. And I'm going to pick the TypeScript version, which defaults to ethers. They are trying to change the default to VM, and there are other projects changing defaults to for VM Foundry, but currently the default for hard when you start it is ethers. When you pick TypeScript, it is ethers. And we're going to see the same example of smart contracts as we saw in lesson 5 of that lock.ts, lock.sol smart contract, right? And the lock.ts script and tests, so that we can see that ether is exactly equal replacement for VM. Okay, let's do this. npx hard init. And I'm going to pick the option of a TypeScript project. Okay, if you arrive at now, before we start on the gas optimization lesson, I'm just presenting Ether.js as an alternative to VM. So I'm going to create this project using TypeScript without VM. Okay. And I'm going to pick all of the default options here.
What was the last command, please?
It's the same thing we did on lesson 5, okay? We initialized the project, we installed hard locally, and we did the init command. Remember that we did that on lesson 5? It was a while ago.
Yeah. Can I see that npm initialization command again, please?
This one here. I'm
No, before
it
that,
right
before that.
This is the installation command. Again, you should see that on the lesson 5.
Yeah.
So,
yes, I remember, yes.
Good. Yeah, so you install hard locally. It's not super necessary for it to be a dev dependency. Okay, you can install it normally there. And then you do the init without picking the VM. In lesson 5, I told you to pick the VM option that we used it so far. Last week, it was clear why we used it. But starting this week, we are also going to use VM again. I'm just showing it this for today, and we're going to use it in a future lesson. But for today, for example, you starting this week, we are going to have both tools for us to use, Ethers and VM. Okay. Good. Marco, please, for all of those questions for past lessons and all, feel free to ask me on GitHub issues, or you can ping me on the technical channels there on Discord, okay? I've seen a surge on people asking questions there. That is great because we can answer that with time, okay? So feel free to reach out. Now, Arda, we pick a TypeScript without VM, okay? Create a TypeScript project without VM.
Also, can you show us the final versions that you got of everything, like Node,
Like this, those files.
No, I mean like the Node version that you're using currently, and NVM, the NPM version. Yeah.
Okay, using Node version 22 and PM11 latest. Okay. So I'm going to show now the structure of that folder. You're going to see that it's very similar to what we have been using with VM. Okay, let's me, you have a question?
Yes, I have a question about this installation. When we install project, TypeScript project with VM, does it mean that we just have a VM pre-installed? It's filled in the package log, or so could we create, for example, like a default project with TypeScript without VM, and later install VM using our package manager? Yeah, it will be the same as in case if we select the type project with VM already installed. It will be two similar projects, or
So
is there some difference?
it's different. Here would be, when we pick this option, would be with ethers. So if you add VM on top of ethers, it's super messy. They don't work very well. It's like you wanted an electric car, or you want a gasoline car or diesel car. Of course, you have hybrids. You have cars that run with both, but then you have two engines and the car is super heavy, you know. So right now we are going to pick either ethers or VM. We are not going to mix both, okay?
Yeah, I mean that in case we choose the create project TypeScript project without VM, and later, for example, we choose to go further with VM, we could install it using our package manager, and it will be the same
It's
in
not going
case
to
we
be the
select.
same. It's not going to be the same. It's going to be super messy, like two heavy dependencies for
No,
the
I mean
same thing, you know?
without others, only. So
Because this is what I'm trying to explain you. When you create a TypeScript project, it is a TypeScript project with ethers. I know they didn't put on parentheses, but it's a TypeScript project
okay.
with ethers.
So by default, it's come project that we
With it,
created now is with others, not
yes,
with. And if we choose with VM, it will come without wizards, only with VM.
exactly. This is what I'm trying to
Okay,
explain.
okay, I get it. Thank you.
Yeah, because the way you're asking, you are thinking like the TypeScript is like in the bare bones, and then you choose if you add ethers or VM, right? But this is not what is happening. When you pick TypeScript, it's not like a bare bones implementation. It is an opinionated implementation with ethers already. So you don't add VM on top of ethers. It is messy. You either pick one or the other, okay?
And in case we select Harhat init, we create the project all with ethers, all with VM.
Yes.
Okay, thanks.
Arda, you have a question here before we
Yeah, one
proceed?
more quick question. So we should probably not ever try to use ethers with VM, right?
Yeah, it's not a very good idea as far as I know. Let me show the project working, and then you're going to take more conclusions on this. I'm going to open this on cursor. just to show the file structure, you could open that on VS Code or whatever IDE that you prefer, especially ones that would have the Marketplace Explorer. Okay, and here is the structure. I have this contracts folder with this log.sol, the same smart contract. Okay, and now we have this test log.ts using ethers. And look how the structure is very similar. We have a log function where I'm getting all of the signers. For example, what we did with VM using get wallet accounts, wallet provider, I guess. And here we're getting something called signers. And then instead of doing the VM dot deploy contract, we have first the creation of a contract factory of contracts. And then I'm picking this factory, calling deploy on it. So VM is doing that with one line of code. Here we're doing it with 2 lines of code. And then later, when we want to call something, for example, unlock time, I don't need to do lock.read.unlock time. With VM, you need to specify it if you want to read or write. Ethers already know if this is a view function or write function, because when we compile, we're going to have something called type chain types that is going to statically type everything here. Put the type. Okay. In scaffold ETH, in the deployment function, we also use ethers. That is correct, Martin. Okay. So this is all the difference. Let me show that for you. I'm going to do a compilation in PX, hard compile. It's going to work exactly the same as we did before. It's going to compile those smart contracts and put in the artifacts. The only difference is that it's going to create these type chain types. That is automated generated code with the typings, the static typings for those smart contracts. It's not using AI, but it's automating the creation of those TypeScript for us. Okay, and whenever we do test, npx hard test is going to do the same thing as we did with VM. So the output, the outcome of using ethers is the same outcome as using VM, just that some of the operations they change. For example, creating the factory for contracts. Before we want to deploy this lock, we create this factory that can be proven very useful in the future. And when we are interacting with a write or read transaction, we call this smart contract directly without the .read or .write. Okay. Questions here? Sounds like a complex operation replacing VS by ethers, but it is just a small adjustment in the code because both are doing basically the same thing. Okay. Yes, let's me.
What is commonly used now in the industry?
That's a great
What
question.
is the most used, like Ether or VM?
VM is getting more used. Yes, it is more like front end oriented than ethers. So when you use the hooks, like Pogme hooks, or even the hooks from VM, it's easier to use that in the front end when using React. Okay. I prefer ethers. I don't use only React. I use all the frameworks. Ethers is great for using all the frameworks for doing backend. Ethers is great for writing tests and scripts. I love ethers. So if we compare both in the technical side, we're going to see a lot of advantages or similar features with ethers. But if we compare on popularity, VM is getting more popular. This is true. I have to admit that. And this is why we saw VM so far. We use the scaffold ETH. If you pick all the startup kits, they are also going to be using VM. So I'm already showing you what is more compatible and popular. But for some things, we are going to need ethers. For example, for today's lesson, showing the gas comparison, ethers is great. For upgradable smart contracts with the hard hat upgrade plugin, we need ethers. For the things we did scaffold ETH, we need ethers. So it is still baked in a lot of things that we are going to use. Okay. So let's start today's lesson content about gas optimization by creating a new contract called gas.sol. This contract that I'm suggesting here. This code happens. And do not try to understand what this contract is doing, like making sense of what this contract is doing. The syntax is very easy to understand. It is the same thing that we used in the past. But this contract is not doing anything useful, okay? It's just some example functions. For example, this loop action, what this function is trying to do, weighted average or something like that, no. I'm just doing some random crazy mathematics just to consume some gas to show some techniques, some this is what I'm trying to say, that this is just a toy function. Okay, do not spend time or attention trying to understand what this function is doing. It's just doing some loops actions. Okay, later we're going to do this update number. Sure, that is basically doing a loop. This is an example for things that we want to do in practice. Okay, tomorrow I'm going to use a more elaborated example, but for today, don't worry about these what these functions are doing. It's just about doing some loops and doing some operations so we can study the gas costs. Okay, and for running these, I'm going to create a script, okay, for deploying, for interacting those smart contracts with the syntax of ethers. Okay, so pay close attention of what I'm doing here, so I can guide you through using ethers for doing those tests. Okay, and we're going to understand what those functions from this gas.sol are doing with these scripts. Okay, so the first script that I'm going to create is this script for comparing compiler option. I can put all in the same script if I want. Okay, I could create different files. I'm going to create a new folder called scripts in the root. The name of the folder is not important, like the test folder. Scripts is just a folder that we are using. They had this folder scripts in the past, and then they moved it for this ignition. I'm not going to use anything about ignition. I'm just going to create a script called gas.ts. The name of the script is not important to you. And I'm going to paste this code. Okay, and here we're going to start playing with ethers. I'm going to show how to fix this smart contract first. This is smart contract, no, this is script first, and then we're going to dive into explanation for today's lesson. Okay. I'm already importing this config from hardhat.config that I'm going to use in the explanation, so you don't need to worry with that. But in those three dots, we have some things to solve first. Okay. I'm creating that function compare deploy, picking those settings. We can ignore this. And then I'm importing get contract factory from ethers to deploy that gas smart contract here in line 13. You see? So I need to have ethers and I need to have the type of gas. This is basically all the complexity that we need to worry for today's lesson with ethers. We were importing VM from hardhat, right? Guess where we're going to import VM from? Hardhat. Hardhat has this option to work with VM. Okay, let me put it down here. Gas is a type. I'm going to type out the contract. I'm going to give it a type of the gas smart contract. But the gas smart contract is in Solidity. There is no way to use Solidity for typing a TypeScript file. Yes, this is why we have this type chain contracts, type chain types. We can import. I had a quick fix for that in the past. Let's see what happened. Maybe I need to open it again after I compiled. Because this is something that the IntelliSense should give you to. You can import this gas smart contract from type chain types. If for some reason IntelliSense is not giving you this suggestion, I can guide you through this too. But I'm going to show that. Inside these type chain types, we have these contracts here. So I did not compile that gas smart contract. That was the problem. Let me compile. Now inside type chain types, I'm going to have that gas smart contract. Compiled. Now inside type chain types, I have this gas.ts. You see? So this is why it wasn't giving me the suggestion. So I'm going to import this gas type from type chain types. If I do control dot or command dot, it's going to suggest me this importing gas from type chain types. And that's all you need to know for migrating from VM to ethers, okay? Now I'm going to use this smart contract factory to deploy this smart contract. I'm going to wait for deployment. How we would do that with VM? We would do public client dot wait for transaction received, and then we would pass that receipt hash. Here with ethers, I can do just that, wait for deployment. And then we can get the deployed transaction received, and then I can log that very easily. With VM, I would need like 3-4 more lines of code. Here, I can log that in lesson 16. I can log the amount of gas used for that deployment. Okay. And then I'm going to write into loop actions. So contract.write with VM, right? With here, no, just contract loop actions. With VM, you would need to pass the arguments in an array, right? With ethers, no, you just pass the argument. Okay, I just need to create this test value. But let's put like 10,000. 1,000 is a good value. So I'm going to do loop actions with this test value. I'm going to wait for that transaction to complete. And then I'm going to log this out. Even the starting code point is here, okay, on lesson 17, Introduction to Gas Optimization. I've copied this smart contract, and now I'm in this script, okay? Good. And if you are asking about the initialization of a new project of the hot, you just refer for lesson 5, and instead of picking the TypeScript with VM, you pick the normal TypeScript. Okay. Yes. Well, let me send me in a message. Let me send it in a group. Did you mean to send that for me directly? Or for the group? Okay, good. Yes. It's the same step that as you have in lesson 5. I assume that you did that dozens of times in this bootcamp already. So nothing new here. And this is the script as we have. What this script is doing? Now we start the subject of gas optimization. This smart contract, when it's compiled and deployed with this bytecode, we are not going to have the Solidity syntax deployed on chain. We saw that on week 1, remember? We are going to transform this smart contract in bytecode, and then the bytecode is going to be deployed on chain. There are several ways to build the same bytecode to do the things that we are asking. Several ways to do this machine code to do the same thing. How to pick a number in the storage and sum it with another number. There are many different ways to do that, okay? And when we are writing the Solidity smart contract, we don't have any control right now, as we're doing here in line 7 to line 12, on how the compiler is going to produce this bytecode. It could do more bytecode, it could do less bytecode, it could put more things, less things, and all. So the only way for you to tweak this as a developer is by using this configuration, this user settings of the Solidity Optimizer. And let me start by presenting you this. The Solidity Optimizer, I have this reference on here. The Solidity Optimizer is a part of the compiler program, an off-chain program that runs there on your computer, that you can pass configurations like these, like the Solidity version and all. And the Optimizer is a program that when you enable is going to run trying to pick the best bytecode to represent what you did there on your Solidity syntax. Okay, it's not going to change what is being done. Okay, it's not going to change the Solidity algorithm, the intelligence of the Solidity code that we're doing, but it's going to change the low-level stuff that is happening behind it, okay, under the hood. So, for example, if we open or referring to that link, if we open a file of the hardhat.config.ts as we have here in this project, hardhat.config.ts, we're going to see this configuration here, hardhat user config like this, and we don't have we don't have any indication, we don't have the optimizer turned on, we don't have any reference for this. So what is going to happen here? I don't have this optimizer settings. I don't have these settings there. I don't have this optimizer settings. So it's not going to log this. It's just going to deploy the smart contract and then log the amount of gas used, and then it's going to log the amount of gas used in that transaction. Okay. A normal deployment of the transaction. There is no complexity to understand here yet. I don't have it configured in my hardhat.config. You should not have it there too. So it's going to run just like that. Let me show that for you. npx hardhat run, then scripts, this gas.ts. Same thing as we did in lesson 8 or so. This is going to, forgot what line of code. What line of code did I forget this before I continue the explanation? Something obvious.
Run this compare deploy. Call it.
You're not
Yeah, I
running
didn't call the function, define. So compare deploy. This is async, so I'm going to do that catch. Whenever I catch this, let me copy that from all the projects as we have. Copied from project. Oh, I have these scripts, should have it there too. So it should have this little syntax here, right? Catch error, then console error and all. I'm going to do the same syntax for today with compare deploy. So compare deploy, catch error, and then if I have error, I'm going to console that. If not, exit code. Let me paste that in the chat. Oh, that's muted that. That's good. You can do then and catch, it makes no much difference, okay? It says async, I'm going to call it like that. Let's run. Sorry, and then returning for my explanation. This is going to run the script, is going to deploy the smart contract, and I'm going to log how much of gas it was consumed when deploying and how much gas it was consumed when running the function. So with these parameters, it consumed 5 million, no, actually 546,000 units of gas and 1 million, no, actually, oh God, 10 million units of gas when running the function with the 10,000 parameters. I guess you should have but 1,000. This means that this smart contract is kind of heavy, okay, for us to run this operation, at least with these parameters. And it uses this much of units of gas, okay? Every unit of gas is related to the amount of work we are processing when running the EVM. Okay, it's not much on the monetary side. It's not much how much we're not about how much we're paying for that gas yet. It's more about how many units of gas we're using. Okay. It's you can do a metaphor parallel with cars. If I say, hey, I used $5 for going from my city to the other city, it doesn't make much sense of comparison when we bring to dollar, because I don't know how much I paid per gas, right? So if I say I spent 5 liters or 1 gallon of gasoline to go from here to there, then you know if it's efficient or not, right? Then you remove the cost of gas from the equation. So for today's and tomorrow's lesson, we are only going to deal in gas, not in the money that we pay per gas, okay? So we deployed that smart contract, and this was the cost for calling it. So far, not much of new content. We did that a few times in the past. We paid for these gas when we deployed to testnets. We got to get money from faucets. We know all of this already. Today, I'm going to introduce the optimizer. We are going to enable it. We're going to do something like this. Let me copy from here. We are going to define this configuration in our hat.config.ts. And we're going to see how this optimizer changes the efficiency, or how it impacts our smart contract. Let's use this same configuration, enable true, runs 1000, and let's run this script again. Now it's going to log that it's using 1000 runs on the optimizer. So compile successfully using 1000 runs, and look, the deployment got a little cheaper from 500 to 478. Let's say 5% cheaper or so. But running the functions, instead of 10 millions, it's now costing only 6.5 millions units of gas. See, 35% reduction or something like that, just by enabling the optimizer. Interesting, my smart contract is now cheaper to call. I'm doing the same operations, doing the same stuff on chain, but now the smart contract is way cheaper to call. So you might be tempted to increase this optimizer even more, from 1000 to 10,000, or why not to 100,000? The more we optimize, the cheaper it's going to be, right? But this is not how the gas optimizer works. The more we tune it up, the more expensive or deployment transaction is going to be. Okay, so by putting 10,000 or 100,000 runs in optimization, we had an even higher reduction of gas cost when calling the function from 65 to 6.5 to 6.47. Okay, a small reduction, but we increased a bit the amount of gas used by deploying. Almost the same as we would use without the optimizer, okay? So when you enable the optimizer, it is an insta-win. You get a cheaper deployment and a cheaper execution. But tweaking the amount of runs, then there is a two-edged sword. You optimize it for more runs, Or if you want the deployment for being very, very cheap, you can put your optimizer to 1 run. So let's say it's a smart contract that you're going to deploy it only once, like a soul-bound token or something like that. Then when you run that deployment, when you compile the project, the smart contract with this compiler option, and when you deploy it, the deployment is going to be super cheap, like 407 instead of 546,000. But the execution of the function got a little more expensive. Instead of 6502741, you have 6502785. So you are paying a little more gas per execution, but your deployment got a bit more cheap. So that is a trade-off here, you see? Okay. Lauren, do you have a question here about this?
It's clear, but I missed some steps. How did you change the hardhat.config.ts file? Sorry.
Sorry, what's your question again?
The hardhat.config.ts file. I don't have this Solidity version setting optimizer lines. Where did you find it? Sorry.
You have it like this, right?
Yes.
Yeah, so you want to change it like that. I've sent that in the chat, and you also have it in this reference. Okay.
Okay, it's in the chat, yeah.
Yeah. Okay, so enabling the optimizer, it's good for saving gas. But for some other things, actually for 99.9% of the things that you want to optimize, the optimizer is not going to help you at all. You would expect the optimizer to search for patterns of optimization in our code, to search for like repeated access to memories, repeated access to storage, and bad memory layouts and all. But actually, the optimizer is not doing that. I'm going to prove for you today. I'm going to leave the optimizer in 1000 runs, and I'm going to see some of these examples as we have in the reference. Okay, gas optimization tricks, and this awesome list of gas optimization sources for you to study. Okay, and we have about 15 minutes only for this subject. I'm not going to go over all of this list with you. It's a gigantic list. It's getting a little outdated. Ideally, we would add and suggest new articles for this list, and you can also search on like gas golfing forums and social media, because gas optimization is a huge subject by itself. There are professionals that dedicate their whole career for optimizing smart contracts. Imagine big contracts like Uniswap, like Aave, like Compound. Every transaction that they do with this smart contract can be spending more or less depending on how they optimize that specific piece of Solidity code. Maybe you are wasting millions of dollars per year because you did a badly optimized smart contract. All of this money could be used for other things, and now it's being used for pumping the bags of the validators, of people that validate those blocks. Okay, it's not that bad, but you are burning cash for the sake of computation. You could be using this computation for better stuff. So, as a rule of thumb, whenever you're doing a smart contract and you are doing more of what is cheap instead of what is expensive, you have a gain of efficiency. Okay. It's not that you should avoid the feature of external function calls. Avoid the feature of writing state variables. No, actually, you need those features. You need those tools for writing a smart contract. But depending on what you want to do, sometimes you can do the same thing, doing more of what is cheap and less of what is expensive. Oh, eggs are expensive, meat is expensive, so let's not eat proteins. No, let's use all the proteins in our diet so that we can have the same nutrients but paying less. Kind of the same idea as a food metaphor. Here, when you are doing gas optimization, you are going to try and find cheaper replacements for the operations that you are trying to do. I have some examples here. Actually, I have one example of this here with this update number and update number optimizer. Imagine you have a loop that you are operating a state variable. So we have this state variable in line 14, and we are doing a loop. We are comparing this count value that we are receiving here in memory, and we are comparing it with this storage value, doing 3 operations here. Then we are writing in memory, decreasing this count value, and then we are increasing a storage value here. If I do that 10,000 times, this is going to be decreased 10,000, and this is going to be increased 10,000. Let's say this number is 0. I pass 10. I'm going to do that 1, 2, 3, 4, 5 times. This order function update number optimizer is doing the same thing. It's just that I save this storage variable into memory first, then I'm doing the loop, and then I'm writing back from storage to memory. I'm doing more operations. Here I'm doing 1, 2, 3, 4, 5 operations per loop. Here we're going to do 1, 2, 3, 4 extra operations, and those 3, 5 inside the loop. So in this function, update number optimizer, we're doing more work. In this function, update number, we're doing less work. So how come doing more work is cheaper than doing less work? Because here we are doing more work with things that are cheaper. We are doing more memory writes and reads instead of state writes and reads. The end result is the same. We took a shortcut. We optimized some other things that we are doing. This is what the article is explaining here. So whenever you can do the same thing as you were doing before with more cheaper operations, you reduce gas costs. And then you need to think on that always, like how I'm going to do this and that. And now not always the most straightforward answer is correct, because you might have some problems with optimizations. Okay, and then we're going to do a script to show that in place. Okay, you have a question, Arda?
No, I actually have the answer to your rhetorical question. Why the optimized is better? Should I say it, or should you run it?
Let's think on this together.
It's because in the unoptimized version, you're reading the memory for whatever the loop runs for every time. Sorry, the storage. But in the optimized version, you read the storage only once, not for every loop index. And that's what's causing the problem, right?
For example, line 19 and line 29. So let's say this one costs $5, the other one costs 1 cent. So even though I'm paying extra $5 here, inside this loop, I'm doing much less. And then at the end, I just do it once there. I just write it once at the end. Okay, it's like doing operations in memory before going to the database, something like that. Okay, so when we run this script, let me paste the script there, compare locations. I'm going to paste that script, that snippet in our script, compare locations. And then I'm going to call it instead of compare deploy, compare locations. I need a test 2. Let me create the test value 2. Let's make it the 10,000. Test 2 value. Let's make it 10,000 too. Why not? 10,000 is a good. I don't know why Copilot is suggesting 100,000. What's the catch here? So compare location. I'm going to deploy that smart contract with this optimization configuration here of 1,000 and all. And you are going to see that even though I have enabled the optimizer is not changing this part of my code. I'm going to show that for you. Which instead of calling the compare deploy, I'm going to call this compare locations now. And look, when I had the storage write and reads for this smart contract, we used 2.5 million units of gas, a lot of gas. But just by rewriting that function to do the same thing in a different way, we used less than a million. Little less than a million units of gas. So writing Solidity, it's easy to start, as we saw in the first weeks, but it's hard to master. Because if you implement the things straightforward as you think, then, or if you just use the recommendations from AI, vibe coding and smart contracts, you are going to have a lot of optimization problems and a lot of security problems, as you're going to see security today too. Okay, so this is gas optimization. Is this clear for everyone? This difference that we had? Okay. 150% more expensive. So we had a reduction of the calculate. So 2.5 minus 0.6 divided by 2.5. We had a reduction of almost 62%. Okay. Just by changing 2 lines of code. Imagine your protocol is paying $1 million in gas per month by running this, and then you present a solution. Oh, let's say I'm going to change 2 lines of code and save $600,000. This is Solidity. This is smart contract development, okay? The second example that I'm going to show today, the second one that I mentioned in this article too, it is even weirder because it's something that is very low level, that Solidity as a high level language, as developers using Solidity as a high level language, we shouldn't need to worry with this low level stuff, but because of gas optimizations and later because of security, we need to know these things, okay? So this is why people invest years of their time learning smart contract development, because there is a lot of complexities under the hood. For example, packing structs. I have in this gas, sorry? It was an open mic, right? I have in this gas.sol example, two strokes inside this smart contract that are exactly the same. They struct packet with object A, B, C, D, like the voters, like the proposals, as we use it in the ballot, remember? And they unpacked, which is the same thing, an A object with a UV256, a B object with a UV228. Imagine those could be strings, booleans, bytes 32, addresses, arrays, mappings, whatever. Those are different objects. Then I have 2 functions. One to create a package object and push that inside an array, and another one to create an unpacked object and push that inside of an array. And if you look here, those objects are exactly the same object. From A to K, Here, they are the same object, the same sizes, the same value and all. They are just organized differently in the code. Like I'm doing this and that. I'm changing the lines of code. Just by doing this, let me show you in the script. Okay, scripts can't lie. If I put that in a test and run, it is the real thing. I cannot lie with this. Let's call this compare packing function. By calling this a create packet, and by calling this create unpacket and then create packet, to see the gas difference of saving the same thing on two different storage layouts. Let me save that script. Let me call it. And I agree if you complain that this is too low level, like too crazy way to handle it. Even though we have the optimizer enabled, just by changing the order of the variables, one operation cost 55,000. Single atomic operation of saving this object cost 55,000, and the other 5,000. Almost 10%, 10% savings here, just by changing a few lines of code, the order of a few lines of code. Why? Because when you save packet structs, when you save structs actually in Solidity, in smart contracts, they are going to group smaller types, like you win 228, you win 96 and all, inside a slot of 256 bits, like some boxes. So if this struct is in line 34 called packet is using 3 words like this, fits a whole 256 block. This fits another, and this fits another. It is cheaper to work with this packet than the unpacket, because you cannot overlap. You cannot start an object in a storage slot and then finish in another. So for example, these here would fit the same storage slot, and then this would fit another. Then these would fit another. If I guess I can put these together. That's the only way to, okay, no, actually I would put these together, and then these would be in the 4th slot. I have some space unused in some of these slots, you see? So this causes the inefficiency. And I would expect the compiler to solve that for me, the optimizer to solve that for me, yes, but actually with Solidity, no, you need to handle all of those little technical details when coding a smart contract if you want it to be optimized, gas optimized. Okay. Questions before we proceed for the next subject? This is the time that you raise your hand and say, oh, this is crazy. Yeah, this is gas optimization. It's a lot of study to this, a lot of work, especially the subject of security that we're going to see later. That would require some low-level study for this. Okay. Everyone arriving now. We have 41 participants. We had 20 a while ago. Sorry, I forgot to warn the last lesson. You received some emails and some warnings, but the time zones in UK changed. Okay, so you might want to go for the recording if you lost a bit of today's lesson. We just finished the first part of today's lesson. That would be gas optimization. Here we have all of the references here. And I'm going to pick from here to explain about security, smart contract security, using this project called Ethernaut. I'm going to get there just in a while. Just before we get there, let's look at this example of a positive and negative overflow and underflow. It's going to bridge those two subjects because I'm going to show how a technical complexity of how the bytecode is made for computing those numbers can change a lot of what is happening at the end, depending on my Solidity version, depending on how the compiler is going to compile that code. Even the same Solidity code can behave differently depending on what is under the hood. Okay? So when I say overflow and underflow, this is clear for everyone. I have those references here, the integer overflow and the arithmetic underflow, not negative overflow. Those are two different things. If you have questions about these, let me know. Okay. Overflowing can be understood as an error or a feature, a behavior about integers, because when you can't count up to a number, it would reset to 0. Okay. Do you have any overflow examples in the real life that you know of? Maybe we interact with this every day and maybe you didn't notice. It doesn't need to be an error. It can be a normal object. Oh, Ivan, you got it too quickly. The clock. The clock is a great example of an overflow. You go from 1 to 12, and then you don't have like 13, 14. Even if you have like a 24 hours clock, even though you end at some point and then you start from 0, right? So it's not necessarily an error. It's a behavior about integers, especially when doing computations, if it's like silicon and all, where we have everything digital. We don't have those analog computations in those smart contracts now, and digital numbers, they are represented with digits, zeros and one. They do have these limitations of overflows. And when doing floating logic, we can have those underflows too, okay? It's different from integer underflow, okay? It is a kind of integer overflow or wraparound in the negative, okay? This is usually they call it a negative overflow, okay, an integer underflow. That is different from the arithmetic underflow, okay? That would be for floating point operations. Do not mistake those two, okay? When we speak underflow, we usually think on arithmetic underflow, which doesn't apply for integers, okay? When we speak for integer underflow, we are speaking mostly like a negative overflow, a wraparound down, and it happens, okay? It is something that we're going to see a lot. Yes, Marco, we're going to see that. You mentioned correctly in the chat. So in the version 0.8 of Solidity, they decided to change the behavior of underflow, not arithmetic underflow. We saw that in week 3, that when you divide, you don't have floating points, okay? So for integer overflow, you would have arithmetic operations to revert on integer underflow, okay, and overflow. Not like floating points. When you divide 5 by 2, it doesn't revert it, okay? It's when you pick, for example, 0 and then you subtract 1, it had this silent change. It would be a major breaking change, but they decided to put it here as a silent change, that the behavior changed. So everyone before version 0.8 would use this package called SafeMath or anything similar to that to check for overflow and underflow. Okay, that would make sure that when you have subtraction, the end result is smaller than this, and it would do those checks for you. But starting with version 0.8, they introduced this breaking change. If you still wanted to do an underflow or overflow, integer, underflow, overflow, you can still use the unchecked block. You pick like this, unchecked, and you do a code there. I'm going to show that in in this exercise. So in what occasions you want to do that? First, for gas optimization, what we just mentioned a while ago. When you know for sure that you are not going to have a possibility for underflow or overflow, and then you can save some gas, because this check for reversion is going to consume a few units of gas every time. So let's say you are subtracting an array position from another array position that you know that is going to be before. 100% sure it's not possible to overflow. Then you can do this unchecked block. Okay, that is going to save you some gas. It's okay to use. A second case is when you want it to overflow, like a clock, like Ivan said. You are building a clock, you want it to wrap back to 0 when going after 12, and Solidity is going to give an error if you try to do that. Oh, come on, it's not illegal. No, it's just the default behavior. So if you want to do this kind of logic in your smart contract, you need to put an unchecked block there, and it's going to start to work again after 0.8. So I have this smart contract called overflow test.sol. I'm going to create it here. Overflow test.sol, whatever name you want to give it. And I have two functions. One called increment to pick this counter that is a type of uint8, so it can store up to 256 values, so from 0 to 255. I'm going to call increment to try and increase the counter by this amount, and this force increment to do this inside an unchecked block. Okay, so this is going to spend little less gas to do this operation, but this also not going to give an error if I try to go above 255. Okay, so let's create a test for this. Overflow.ts for testing that behavior. And we're going to fix this test, the things that we learned in the few first minutes of today's lesson, by importing this overflow test from type chain types and importing ithers from hard hat. Okay. I'm going to compile this smart contract that I have just created, compiling the project. You can compile here from the terminal too, the same thing. Okay. After I compile, I can import this overflow test from type chain types, and I can import ethers from hard hat. Okay. Here I'm using this before each hook, but you could be using a fixture. Okay. It's compatible with ethers. Okay, just that here I want to go straightforward for the test, so I'm creating this contract overflow test, putting there in memory, and every time I'm doing a test, I'm deploying that again. This is what the before each is doing for us, okay? So when incrementing on the safe circumstances, for example, I have the safe increment of 99, for example. So when in the increments correctly, so I'm going to pick this test contract. Let's see if Cursor can do that for me. No, that's test. That's wrong. Yeah, actually it's correct. I just need to import. The ethers package was much more used than VM in the past years, like 2 years ago, 1 year ago. So it's more often to find the GPT suggestions correct with ethers than with VM. VM was more recent. There's no much training data for them unless you're using recent models. Your AIs are mostly going to work with ethers. Okay. So let me add this declaration for expect. I'm going to import expect from chai. Expect from chai. And I'm going to work with this declaration here. Okay, someone wanted to ask a question, just hang for a minute. I'm going to get to your question just in a while. Okay, so expect thing type, and I'm going to tweak this code a little. So the initial value, I'm going to use save increment here. Okay, I'm going to wait. The final value is this, and I expect the final value equal to the initial value plus the save increment. Okay. Big int 99. So let's use big ints here. Good. Who was willing to ask a while ago? Someone? Trust. Yes, you want to ask, Trust?
Yes, yes, yes. I wanted to ask because I noticed that it has like, and initially we started with VM. I wanted to know if you can use both ETAS and VM like in the same
Trust,
project.
your microphone is a little off. Maybe you want to type a question, and then I can read it from the chat. I can't hear anything when you speak on the mic. So here I'm doing this function call with ithers, calling this increment on the, let me close the other files. On the overflow test, it is using a uint 8. It has a 0 there at the beginning. I'm going to increment 99, and it's supposed to work. If I run this test here, maybe I want to put the mock test extension to work. I'm going to see it working, right? You remember how to configure the mock test extension? You need to create that mock rc.json and create that file. Something like that was incorrect. Let me go for the hard documentation real quick. Remember the link where it is. I'm going to configure that. You have that from lesson 5. I'm going to create this mock rc.json with this content. We did that quite a few times in this bootcamp, and I just lost control. Hello, sorry, bad joke. I'm going to put this mock rc.json, and then I can load that with mock test explorer. Okay, so I'm going to run this. So when doing the save increment, I expect the transaction to work and the final value to be equal to the initial value plus the save increment. Okay, I can even place a breakpoint here. I can debug this test and see the final value as needed. Okay. Okay. Trust, we're not going to use both in the same project. Okay. That was the explanation in the first 20 minutes of today's lesson. So we're going to use ethers just for today's lesson for you to see the gas cost and all. So the final value that we have stored is 198 equal, that would be equal to picking the safe ether. Sorry, Trust, I couldn't understand anything from your mic. Maybe you want to ask in the chat. That's going to be best. Okay. So returning here, we are passing the safe increment. We had the initial value of 99 in the beginning. So doing a safe increment of 99 gives us 198. which is good. We can store that in a UH8. Okay.
Could you
But
show
what
me
if
sorry, could you show your imports in this file?
those two imports, type chain types and eachers were imported with IntelliSense, and Chai gave us expect. Okay. Good. We saw this type chain types in the last script we run, importing eachers from Hot Hat as we did with VM. Okay. And Chai as we did a few times before. So when incrementing to overflow, it reverts. So see if Copilot can do that quickly. I'm running out of time here. Maybe I should prepare more of these snippets. So I'm going to have this initial value. I don't need that actually. And I expect the test contract when I try to increment with unsafe increment to be reverted with this panic. I can just do to be reverted. Don't need to go that fancy, right? We run this test here because it was working. Just to clear that red stuff. Okay, so it is working in the next one. It reverts. So when I do this operation, it should revert. It reverts. Okay. How to see the reversion? I want to touch on it. So you can drag this await block inside the expect. Instead of await expect, you're going to expect await. And then if you run this test, you're going to see the problem coming. When you try to increment 199 over 99, you're going to have this error, VM exception. Reverted with panic code 0x, the arithmetic operation overflowed inside an unchecked block. Okay. So this is why we await expect instead of expect await. Okay, and when incrementing to overflow within a checked block, this would be similar to that first one. Let's see how. I'm going to paste that for you in the chat. Force increment. It did correctly. That's nice. So let me copy this for you. And let me copy this other one for you. When using this force increment, run this and that. When you're running this force increment, it's going to use the unchecked block, and we can make it go back to 0. Can make it go back to the you can do an operation that wouldn't fit in the size of that object, and still it works. Okay, what would be the final value if I do a console log on this final value? Overflow. No, I just want the final value. Console log, just final value. Do you know what this final value is going to be? Give a look here. I'll try and think around this problem, make some guesses. We had 99 as the initial value, and then we sent a transaction, try to increment it by 199. It would cause an overflow. This is why we tested this thing, and it is reverted with that panic code. So how much is going to be the final value for this? Suggestions? Guesses?
Would it be 0? The overflow to 0?
Well, let's think on that. Yeah, unchecked block is going to let it overflow. But then when doing this overflow operation, is going to try and fit the result in what we had there in the beginning, in the space that we had in the beginning. And the Wnt8 would store 256 values. So anything that we have as a result is going to be truncated up to 256, right? So if we look at the watch right now, for example, here on my side, it is 11 and 22. It only fits 12 hours, right? So if we add 5 hours to 11 and 32, what hour are we going to have? It's not 0, right? We're going to have some result. If you're using a 24 hours clock, it's going to be like 14 something, good. But if you're using a 12 hours clock, it is going to go back to 0 and start adding. So Ivan got the conclusion that 199 plus 99 is 298. If you go back to 156 positions, it would give us 92 for 42 actually, which is a great number. Maybe this is how the supercomputer calculated the answer for the life, universe, and everything. So let's see if the final value is 42, the meaning of life. Now everything makes sense. Maybe it was just an overflow error. Okay. Got the reference. And last but not least, I wanted to introduce the subject of the smart contract security too, especially this one about overflow as a first first example, as a first instance of security flaw that can happen in Solidity. A lot of hacks happen because of this. Okay. I would suggest this documentation first on the known attacks for you to read it through. I'm not going to do it today. I'm just trying to introduce you to these subjects in this bootcamp. I'm not going to do a whole lesson on that. We have advanced Solidity bootcamps with Encode too, where we have these explanations more in depth. But knowing that these exist are great, like race conditions, reentrancy, DDoS, MAV, and all of these kind of topics are great for us to get started with the subject of smart contract security. For this bootcamp, I'm going to suggest Ethernaut as our guide, because it's a fun game, engaging game that you can pick some challenges. I would suggest these 3 for us to do in this bootcamp. If I had time, I would do them live. I'm going to do just the challenge 5 for today. But if you do all of those challenges, you're going to get to know all of those known attacks that are listed here in a very fun and engaging way. For example, Ethernaut lesson 5. I'm going to connect my MetaMask account for us to play. It interacts with some on-chain contracts. We can deploy some honeypots contracts there and interact with them. So I'm going to connect with my MetaMask account. Another very important step is to switch for dark mode. The light mode attracts bug. So you go there for dark mode. And you have those 33, actually 34 challenges. The first one for you to get started to understand the structure, how to use the console now, and all the orders for you to interact with these smart contracts. So for example, exercise 5. This challenge proposes a token contract, this token contract, okay? And I'm going to deploy this instance. Let me show here in the terminal. Okay, this is my interaction with this game. And I'm going to get a new instance. A smart contract is going to be deployed with this code for us to try and hack that smart contract. I need to pay for that deployment, so I'm going to pay for that from my wallet, but then I don't get to alter the code of that smart contract, okay? This is the game I'm playing, so I receive the game as it is. And this is the smart contract that I have. This is the code of the smart contract. And it was deployed for this address. You see here in the chat, when I click this get new instance, it prints for me here in the terminal. So now I could write a script with hat. I could use remix. I could interact with it using scaffold ETH. There are many different ways for me to play this game. I'm going to pick remix because we are almost out of time. So I'm going to use this code of the smart contract that I have, this Ethernaut challenge 5 token code, to attach this instance using remix. We did that in week 1, remember? We deployed the Hello World contract. You did that in the homework too. You deployed that smart contract and interact that with it with remix. So I'm going to create a new smart contract. Token.sol. I'm going to paste this code and I'm going to interact with it using remix with my injected provider. The address is this one that I have here in the chat, and I'm going to attach to this address. So with this smart contract, I can see that I have a total supply here, and this is the total supply, 21,000, blah, 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 and I have a balance. My balance inside that smart contract, let me pick my address here, because I have it here too. Yes, I do have. So let me copy my address. My balance inside this smart contract is 20 decimal tokens here. I would win that game if somehow I can manage to get more tokens, preferably a large amount of tokens. And I don't have a DEX, I don't have exchange, I cannot change the code. The only thing that I can do is make a transfer transaction. And I can't even transfer more than what I have, because if I send a value that is higher than my balance, for example, if I send 21 tokens and I only have 20 tokens, it's not going to be higher than 0, right? Or wrong. I'm going to take 1 extra minute in today's lesson just to get to this. What would happen if I would transfer someone else 21 tokens? I only have 20, but I'll try to send 21. What is going to happen here? In solidity 0.6, it's not 0.8, 0.6. Any guesses?
I think I know the solution to your problem. If you let this balance minus underscore value underflow, it's going to be greater than 0.
Yes, because we are not going to have a negative value here. For solidity that runs in the EVM, this is going to be positive. It's going to be higher than 0. So if I try to transfer someone else 21 tokens, let's see what is going to happen. And we make this transaction. It might take a few seconds for it to confirm. I can show that on tomorrow's lesson too, the result. But this is going to cause a state change that is going to update the balances of that person with this value okay? And it's going to decrease my balance with that value. Well, let me show this state change on Etherscan. It's still indexing. Okay, maybe I should show that tomorrow for you. I'm going to paste that hash in the chat, and we start from this tomorrow. I wanted to present OpenZeppelin so that you now see how the game works, you know the mechanics of the game. And as a homework, optional homework, of course, you can pick some challenges, those three challenges that I suggested, and start playing with it. Okay. Sounds good. If you have questions, please feel free to reach out to me. Create issues on GitHub, reach out to me on the technical questions channel in Discord. Okay. And we get from there. Sounds good. Thank you, everyone. Hope you have enjoyed today's lesson. See you tomorrow for more. Bye-bye.